Let's revise the whole topic of energy in GCSE Physics. First thing that we need to define is what is a system. Well, this is just one object or a group of objects. For instance, a system might be a couple of masses. Let's say this one here, which might be 5 kilograms, and then another one which is 1 kilograms. Essentially, whatever we're given in the question. One of them could be moving at, say, 5 meters per second, the other one might be at rest, etc. Now, when a system changes, the way energy is stored also changes. Let's have a look at some examples. For instance, if we were to project an object upwards, so let's say that we have this object and then we throw it upwards. What's going to happen is that initially this object will have some kinetic energy that will be decreasing. So as the object is going up, the kinetic energy will be going down because the object will be slowing down. And at the maximum height, the object will have gravitational potential energy. On the other hand, if we have an object that's colliding with an obstacle, so we can have something like a car. Let's draw a little car across here. And let's say that has a collision. If that's the case, the kinetic energy of the car that is moving this way will be dissipated into the wall in things such as thermal energy and actual work done on the wall and damage to the wall and sound energy as well. We can also have an object which has been accelerated by a constant force. So we can have a similar car like so, and let's imagine that there's only one constant force that's acting on it. Let's call that F. If that's the case, the kinetic energy of the car will be increasing. We can also have heating up water to boil, in which case the energy, typically electrical energy, if it's an electrical kettle, will go directly into raising the temperature of the water. So kinetic energy is the energy of movement, and we can calculate it using the following famous formula. Kinetic energy is a half times the mass times the speed squared. Mathematically, we can express this typically with this symbol. The kinetic energy, EK, you could also use KE as well, is equal to a half times the mass times the speed squared. And typically we give this symbol here to be V. Now let's apply this to a little problem. We have a car with a mass 1200 kg, is traveling at 10 meters per second. Calculate the kinetic energy of the car. Okay, well, the kinetic energy is just equal to a half mv squared. Now the mass goes just here, so this will be equal to a half times 1200 kilograms multiplied by the speed squared. A very common mistake is to forget to square the speed. Remember, if you see a square here, just remind yourself that you're going to need to be squaring this in your calculator or later on. So this will be equal to a half times 1200 times 100, and this will give me 60,000 joules. Now let's talk a little bit about the units of the previous equation as well. So kinetic energy, because energy is measured in joules, then this guy here, the kinetic energy, will be measured in joules. The half has no units. Mass is typically measured in kilograms, although you may encounter other units and you need to convert. And the same with the speed, which is typically measured in meters per second, and the actual units of v squared will be meters squared seconds to the power of -2. Let's do a slightly trickier example of kinetic energy. So we have a car of mass 1100 kg moving, and it has a kinetic energy of 40,000 joules. Calculate the speed of the car. Okay, so let's start off with our equation for kinetic energy. It's a good starting point, so that's equal to a half times the mass times v squared. Because we're looking for the speed, we are going to progressively rearrange for v squared. The first thing I'm going to do is just get rid of this half, so I'm going to multiply both sides by 2, so I'm going to get twice the kinetic energy is equal to mass times v squared. Now let's divide by the mass, and we're going to get 2ek divided by m is equal to v squared. And finally, all we need to do is just square root this expression. We're going to get the speed to be twice the kinetic energy divided by the mass. Now the kinetic energy is given here, so that's just 40,000 joules. The mass is also given, so we can plug that into here, meaning that we could easily find the speed, which will be given by the square root of twice times 40,000, then divided by the mass, which is 1,100. And if we plug this into a calculator, we're going to find around 8.5 meters per second. Okay, now let's move on to a different type of energy, which is known as elastic potential energy. This is given by the following formula, that the elastic potential energy is a half or 0.5 multiplied by the spring constant multiplied by the extension. The elastic potential energy is measured just in joules. The half doesn't have a unit. The spring constant is actually measured in newtons per meter. Every time you see the division sign, that actually means per. So newtons per meter. The extension is just the amount that we extend the spring. For instance, if I have those two springs, this one here is unstretched, so it has an extension of 0. So we could even write for this one that E is just equal to 0 at this point. However, if we attach a mass to it, the amount it will differ from that essentially equilibrium point will be some amount E. It could be, I don't know, it could be 10 centimeters or a different amount, etc. But this here is the extension. So it's the extension squared. Mathematically, we could write this as E subscript E, elastic energy, is equal to a half times the spring constant, which is typically given K, multiplied by the extension, let's just call it E squared. Sometimes, particularly if you're doing A-level, you may see the extension written as X, which happens quite commonly. And let's apply this to a problem as well. Calculate the elastic potential energy of a spring constant 0.25 newtons per meter and an extension of 10 centimeters. Okay, so let's start off just by writing our equations. So we know that EE is equal to a half KE squared. Now we know that our spring constant is 0.25, so this will be equal to a half times 0.25. Pay attention that the centimeters are not a standard unit, so we're going to convert those to meters. So 10 centimeters is actually equal to 0.1 meters, so that's going to be 0.1, all of it squared. And if we plug this into a calculator, we're going to get around 1.25 times 10 to the power of minus 3 joules. And let's also talk about gravitational potential energy, which is just equal to mass times gravitational field strength multiplied by the height. The symbol for it is normally just EP, and this is equal to m, the mass, times g, the gravitational field strength, or the gravitational acceleration, that's essentially the same thing, multiplied by the height, h. Let's do a sample calculation example. So imagine that we have some sort of a mass which is, should we say, 50 kilograms. And let's say that this is at a distance of 5 meters to the Earth's surface. So this here is the surface. How much gravitational potential energy does it have? Okay, well, all we need to do is multiply those numbers. The value of G, by the way, will be always given in a question, and depending on the exam board and depending on the question, we typically write that G is equal to 9.81 newtons per kilogram. You may be given the value of 10 to approximate things better as well. But yeah, it will always be given. The mass, by the way, is always measured in kilograms in this equation. So should we just write these down? The height is measured in meters. G is measured in newtons per kilogram. It can also be measured in meters per second squared, which is exactly the same thing. And the potential energy is always measured in joules. Okay, now back to our example. So our mass is just 50. Let's take G to be 9.81 meters per second, multiplied by the height, which is equal to 5. And if we were to multiply those numbers out, we're going to get around 2,453. And let's just round those up to around 2,450 joules up to 3 significant figures. Now I want you to imagine that we're heating up some water, maybe in a kettle or maybe with a Bunsen burner. You can see that with my professional drawing right across here. What will the amount of energy that we're inputting into the system actually depend on? Well, first of all, it will depend on the mass. So the change in thermal energy, which mathematically we write with a little delta, this delta just simply means change, will be proportional to the mass. Think about it, if we're heating up, I don't know, the ocean, we would need a lot of energy. Whereas if we're heating up a cup of tea, we would need a little bit less energy. Will also depend on the change in temperature, which typically we write as delta theta. Whenever we use this symbol, this is normally used in physics to represent change in temperature in degrees Celsius. Will also depend on what we're actually heating up, and there's a property that's specific to each material, and that is known as specific heat capacity, which is typically given the symbol C. And there we have it. This is our formula for the change in thermal energy. It's mass, which is just measured in kilograms, multiplied by specific heat capacity, which kind of has a funky unit. It's just joules per kilogram per Kelvin or per degree Celsius, like that, multiplied by the change in temperature, which is typically given in degrees Celsius. Let's apply this to a problem. How much energy does it take to bring 500 grams of water from 20 degrees C to 80 degrees, and we're given the specific heat capacity of water. Okay, so as we wrote above, our equation for the energy is mc delta theta. Okay, we'll pretty much know everything that we need to know. Our mass though is given in grams, so 500 grams is just actually equal to 0.5 kilograms. So I'm going to be careful with that. So the energy will be equal to 0.5 multiplied by the specific heat capacity, which is 4,200, multiplied by the change in temperature in degrees C. Okay, so we're going from 80 to 20, so this is equal to final, take away initial, like so. And if we were to plug these into a calculator, this will give us 126,000 joules. Before we move on to the next topic, I would like to show you a little trick. Now, change of energy is equal to mc delta theta. If we were to rearrange for the specific heat capacity C, we're going to find that this will be equal to our energy divided by m delta theta. Well, this actually leads us directly to this definition of specific heat capacity, and that is the amount of energy required to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. Okay, well, let's talk about power next. Power is defined as the rate of energy transfer, and it's typically defined by the amount of energy transfer divided by the time. Mathematically, we would write this as the power is equal to the energy that's been transferred, which is just E, and then we're going to divide this by the time that's elapsed, which is T. The unit of power is the watt, which is the subject of many jokes of physics teachers. What is the unit of power? Moving on, the energy is given in joules and the time is given in seconds. Because of that, we can actually write essentially the watt as a joule divided by second. So we can say that 1 watt is equal to 1 joule that's been transferred per 1 second. Alternatively, we can also define the power as the work done divided by the time, because the amount of energy transferred in physics is actually equal to the work done. So we can also say that power is equal to work done divided by the time that's elapsed. In this case, the power is also measured in the watt, the time is measured in seconds, and the work done is actually also measured in joules. We can typically demonstrate the definition of power using the following example. Imagine that we have a couple of electric motors. So this here is once again my professional drawing. We have electric motor 1 and also we have electric motor 2. If electric motor 2 is bringing up this weight at a higher speed, this means that it's applying more power, it's transferring more joules per second into lifting the weight. So in this case, the higher speed would actually indicate more work done or more energy that's been transferred, per second. Therefore, well, that means that electric motor 2 will have a higher power. And of course, talking about energy, we have to mention the famous principle of conservation of energy, that energy cannot be created or destroyed, but can only be transferred from one form to another. Now, in the case of our electric motor that's being used to lifting up a weight upwards, the electrical energy, because this thing here is an electrical motor, it will be connected to a circuit, is being converted to the kinetic energy of this block that's being lifted upwards, but also to its gravitational potential energy, because if the block comes, let's say, here, it will acquire some gravitational potential energy as well. And this here will be known as its useful energy. So we can even label this, that this bit here is useful. Some of the energy, though, will be wasted, and this is the type of energy here. Typically, this is due to friction, sound, or thermal energy. In the case of friction, typically we can use lubrication, so something like applying oil to any moving parts to reduce the friction. In terms of thermal energy, in different situations, we can also use insulation to prevent energy escaping into other components of the system. For your GCSEs, you guys also need to know about this property, which is known as thermal conductivity. In general, the higher the thermal conductivity, the higher the rate of energy transfer. So something like a piece of metal, for instance, has a very high thermal conductivity, and this means that if we were to, let's say, heat up one end, then the energy will spread very, very quickly, and then soon the whole piece of metal will get quite hot to the touch. Now, if you have something like a building, the rate of cooling is affected by two things. Number one is the actual thickness of the walls, but also the thermal conductivity of the material. This is why something like double glazing, for instance, in windows is very effective, because air has a very low thermal conductivity, relatively speaking, which means that the building will not lose its heat. Talking about losing heat, let's mention efficiency. Now, the equation for efficiency is just the amount of useful energy transferred divided by the total energy input. Just a little note that sometimes you may come across this equation with brackets and then multiplied by 100 if you would like the percentage efficiency. So you can also use exactly the same equation with the power output. So efficiency is the useful power output divided by the total power output. And once again, if they ask for that as a percentage, all we need to do is essentially multiply by our answer by 100. Let me show you. So we have a light bulb which takes in 60 watts of power, and it only transfers 6 watts to light energy. This means that the light bulb is actually losing 54 watts. Find the efficiency of the bulb. Okay, well, our efficiency is just equal to the useful energy, which, so let's just write that down. Efficiency will just be equal to the useful energy, which is 6 divided by the total output, which is 60, which is equal to 1 over 10, which is equal to 0.1. The efficiency doesn't have a unit, once again, unless we find it as a percentage, and if that's the case, we'll just multiply that by 100. So 0.1 times 100 will just give us 10% efficiency for this case. And finally, let's talk about the national and global energy resources. Starting up with fossil fuels, which tend to include coal, oil, and gas. Now, these are non-renewable energy sources, and they tend to be very, very bad for the environment. So let's just make a little note here and say that these are non-renewable. This means that there's a certain amount in the world, and once we've used all of them, there won't be any more of those. And they have a very bad environmental impact. So they contribute to global warming, for instance, by increasing the CO2 levels, and additionally they produce loads of harmful emissions which have been linked to loads of health problems and are just generally quite bad. We also have nuclear fuel, biofuel, wind and hydro plants, geothermal, and solar energy. Now, those here are examples of renewable energy sources, meaning that, for instance, wind and hydro plants, obviously they rely on the wind, which is a resource that we can use again and again and again, and the same with geothermal and solar energy. Okay guys, well, we've covered the whole of the energy topic in GCSE Physics, and what you need to do is have a look at this video right over here, which will cover the whole of another topic.